Hey, everybody. I want to do a quick review on a chapter that's commonly known in anatomy and physiology classes. It's known as a fluid balance and electrolyte chapter. And usually the chapter is slid in right after whatever chapter you go over the urinary system with. And something that you have to remember is that every cell in your body has fluid inside of it. And the cells of your body are surrounded by a fluid. And so if a cell wants something, it's probably going to pull it out of a fluid surrounding it and then bring it into itself, which has fluid as well. We usually refer to substances or fluids that are inside the cell as intracellular, and we usually refer to fluids that are outside of the cell as extracellular. So we kind of want to talk about that balance, except what we're going to get into is not the cell biology of it. The cell biology of it makes you look at the individual cells themselves and see how things get in and out of the cell, but we're past that. What we want to talk about is we want to talk about the fact that the cells have been doing their job. They have been responding to what's inside your body. And now your body has to control the fluids and the electrolytes overall due to the fact that the cells have been utilizing these substances and the cells have been sending some of them in, some of them out, some of it's been transferred in your blood. And that's just one big fancy way of saying, okay, look, I drank a bottle of water. So what happens with that water? What does my body decide to do with that bottle of water? That's what this chapter is really all about. So I'm gonna go ahead and get started. And I'm gonna pull up the screen share. Uh, and I want to take you to a particular set of PowerPoint notes here. And I want to get us started actually on slide 16, which of course is this. Slide 16 really gets into showing you that we see a picture here and we see this lady who's holding a bottle of water and a tennis racket here on the side. And what she's trying to innuate is that simulate that she's being active. And when your body is, and I just killed that word, is insinuate, but that's what I get for recording a video when I'm tired. But what she's trying to get across to us is that she's active. Okay, so because she's physically active, the cells in her body are going to use the water and electrolytes that entire time that she's active. Over here on the left side, we can see that she's putting fluids and electrolytes back into her body. So let's say every day this person eats and drinks about 25 milliliters of water a day. That's 2.5 liters of water. Most of that water is made up of what you drink and what you eat. And then a 200 of those milliliters are made up of metabolic water. So like when activity happens in the mitochondria of your cells, a byproduct of the aerobic metabolism that happens inside the mitochondria inside your cells, a byproduct of that is carbon dioxide and water. So out of the trillions upon trillions of cells that you're producing, they produce a maximum of 200 milliliters of water every day. While the rest of all this water, 25 milliliters of your water, you're losing every day. And guess what? Here's the funny thing. What we're seeing here is we're seeing her holding a bottle of water and a tennis racket in her exercise clothes saying, hey, yeah, look at me. I'm losing 25 milliliters a day. Dude, you can lose 25 milliliters by doing nothing because you don't have to be exercising to breathe out. This is expired air. This is exhaled air. You notice that the air coming out of your mouth and your nose is moist. So that moisture has water in it, and that water came from your body. Sweat. So you may not be active and you may not sweat today, So you get a chance to walk away with 100 milliliters, big whoop, but you lost 300 just by breathing. Cutaneous transpiration. Notice that's different from sweat. Sweat is what you do when you're hot. It's what you do when you're nervous. It's what you do when the thermoregulatory center in your body is trying to balance out body temperature. Cutaneous transpiration is simply nothing more than the water you lose on a day-to-day basis because you're alive. Remember, your blood is 100.4 degrees Fahrenheit. So the water in your blood will wind up wind up dissipating. It'll wind up leaving your body, evaporating. And that's that cutaneous transpiration. Fecal matter. Fecal matter will take 200 milliliters right along with it. Remember that the large intestine, the job of the large intestine is not only to compact and compartmentalize the fecal matter, but it's also to reabsorb any water that you use to digest the food stuff. So you'll lose 500 milliliters at least through your urine. I mean, you don't really have a choice with that. All the rest of the stuff you can kind of say, well, I'm just going to hold everything in until the next day so I can throw his numbers off. Well, you're going to have to do number one. You're going to have to potty and release yourself. And of course, there's if you add up both the urine obligatory and urine facultative, that's 1,500 milliliters. You're losing 1,500 milliliters just from urine alone. So let's move forward and let's talk about electrolytes just a little bit. Electrolytes are these molecules that are floating around in your body solution. So they're floating around in your bloodstream. They're inside the fluid inside your cells. They're inside the fluid outside your cells. And a lot of times we have to break down these solutes, these molecules that are floating around in your body. We break them down into non-electrolytes and electrolytes, which is easy. Non-electrolytes are anything like glucose and amino acids. These guys are mostly covalent bonded organic molecules. They are molecules that are put together because they're sharing electrons. These molecules, they usually don't dissociate in a solution. So just because I put it in water doesn't mean that it's going to dissolve into a brand spanking new thing. Whereas electrolytes, as soon as you put them in water, they dissociate, they break apart, kind of like sodium chloride. Stick sodium chloride in the water, the sodium and the chloride ions they go away. They separate immediately. And we use these electrolytes. Our cells use these electrolytes every single day, every moment of the day. You're using electrolytes like sodium and chloride and manganese and magnesium and calcium and potassium. And you're using all these electrolytes all the time. So we're always having to keep an eye on how many electrolytes we have in our body. And we're having to keep an eye on how much fluid we have in our body because our fluid actually carries those electrolytes. So this is very important. So like in this slide, you'll notice it talks about fluid intake and fluid output. Fluid intake, if we bring more fluid into the body, our blood pressure is automatically going to go up. Why is that? Because if I drink a bottle of water, I'm going to digest that water. That water is going to be absorbed from my small intestine into my bloodstream. And when that water enters the bloodstream, it's going to mix with the other water that's in my bloodstream. And anytime you increase blood volume, blood pressure goes up. And of course, we see that there's a decrease in blood osmolarity. What that means is if I bring water in, the volume of water increases, but those plasma proteins in there don't increase. And so now that we have more water, it dilutes the concentration of plasma proteins, therefore dropping blood osmolarity. However, with fluid output, as we see fluid leave the body, we can actually cause the blood pressure to decrease. And we see this when someone has high blood pressure and they're at the hospital and they give them diuretics, and the diuretics causes that person to urinate more often than normal. And the reason why is because you can get rid of a lot of fluid out of your body just by urinating it out. Also, this is now going to increase blood osmolarity because now we've decreased the amount of water, which therefore makes the solution in your body have a higher concentration of these plasma proteins and um, other solutes that are in the solution, therefore increasing osmolarity. Now, here are some basics when you're studying a chapter like this, and they're real basic, but there's things you just got to remember. Number one, cells can't move water by active transport. Okay, it's passive in response to osmotic gradients. So cells can't move water by active transport. Number two, fluid balance and electrolyte balance are interrelated. Okay, so in other words, water is going to go where salt goes. So if I take salt out of my filtrate inside of my nephrons, water is going to want to follow that salt out of the nephron. If I have salt coming in to my body tissues and into my body fluids, then the water that was over there with that salt originally is going to flow and follow the salt as well. The body's content of water and electrolyte increases if gains exceed losses, and it decreases if losses exceeds gains. We're going to kind of talk about that line a little bit today. And when about water, plasma volume decreases, electrolyte concentrations increase. Because remember, plasma is 92% water. So, any because 92% of plasma is nothing but water. Where do you think you got that water from in order to urinate? You got the water from your blood, which got the water from other places. However, all those other places contribute their water to the blood. And now and now you coming in calling it to the kidney and calling that blood to be filtered, which means that if water goes out of that, then the concentration of electrolytes in the blood is going to be increased. It's kind of like taking Kool-Aid and being able to have the magical power of taking a lot of the water out of the Kool-Aid. It's going to make the Kool-Aid a lot sweeter. Did we add any sugar? No, we just took water out of the Kool-Aid. Well, why does it taste sweeter than it did before? Because when we had more water in there earlier, it diluted the sugar. It made it less concentrated. But when we took the water out, it allowed there to be a smaller volume of space that the sugar molecules are taking up, therefore making it far more concentrated. And the last tip is when the body loses electrolytes, electrolyte concentrations decrease. And water is also lost. Now, that's something that's very key, that last part. You got to remember that if I turn around and I throw away electrolytes, yeah, the body experiences a drop in electrolytes. Is that the most important thing? Second most important thing. The other thing is that water goes where electrolytes go, especially things like salt. So when the salts leave, the water leaves along with it. Let's see. I want to see where I'm going. There's an image that I want to pull up, and this image is it does a pretty good job of summarizing some things here. It, they have it. They start with number one here at the top, and they talk about the stimulus there, and the stimulus here is low blood pressure. All right. So something sympathetic division stimulation. Um, let's start at the beginning of this. For some reason there's low blood pressure, and that's not always a bad thing. Um, it may simply be low blood pressure because you're taking a nap. So you're in there and you're taking a nap, and so your blood pressure drops. Okay. It's not the end of the world. It just means that, your blood pressure is lower than it's used to it being previously. So now it's got to do something about it because your kidney's ability to be able to create filtrate rises and falls on blood pressure levels. So you notice that the first thing that happens is that there is a receptor in the kidneys at the nephrons, specifically at the juxtaglomerular apparatus. Man, I'm having a hard time pronouncing things, but I won't lie to you. I am pretty tired. Um, and I've always noticed that when I get that tired, words start to slur. Well, anyway, so the juxtaglomerular apparatus, which is a unique little area just at the nephron near the renal corpuscle, or the renal capsule, as some people call it. There's a cluster of cells made up of cells from that PCT, I mean, not the PCT, but the DCT, the distal convoluted tubule, and cells there at the afferent arterioles. And what essentially happens is that the cells in the juxtaglomerular apparatus, they respond to the stimuli, which is easy because low blood pressure can be monitored um, at that place. So they respond to the stimuli. And then the very next thing, the apparatus releases a enzyme called renin. And when renin comes in, there's already this inactive hormone floating in your blood called angiotensin, uh, and excuse me, angiotensinogen. And when angiotensinogen comes into contact with renin, that enzyme, it cuts it, it transforms it, it converts it from angiotensinogen into angiotensin 1. And the minute that happens, it runs into an enzyme that is also floating in your blood, which is ACE, angiotensin converting enzyme. And that turns it into its active form, which is angiotensin 2. So some people look at this and they're like, this looks crazy. How am I supposed to follow this? Well, some of this stuff is already floating in your blood, like the angiotensinogen and the ACE enzyme. That stuff's already floating in your blood. It's just, it hasn't been unlocked. It hasn't been activated. So that stuff's just floating around. But once you drop some renin into your bloodstream, that starts the party. Everything gets started, and it starts this cascading process that ultimately leads you to having angiotensin 2. And angiotensin 2 as a hormone has numerous different targets to help you get the blood pressure back up. One of which is to stimulate the adrenal cortex of your adrenal glands into releasing aldosterone, which aldosterone targets the nephrons and tells the nephrons to reabsorb sodium. Well, when you reabsorb sodium back into the bloodstream, guess who follows? Water, because water follows salt. It's hoping that by adding water back from your kidneys back into your body tissues, that's actually going to bump up the blood pressure in your body. Another target area is the hypothalamus, which the hypothalamus is ultimately going to release ADH and then store it there in the posterior pituitary. ADH is antidiuretic hormone, and then you can wind up seeing how it's almost like it's saying, okay, look, I need blood pressure to go up. The only way to get blood pressure up immediately is to make blood volume go up. So we're going to release ADH, which is antidiuretic hormone. It targets the kidney's nephrons and tells the nephrons, I need you to reabsorb that water that you originally was going to throw out as urine. Another thing that it's going to do is it's going to activate the thirst center in your hypothalamus. Remember, you have a hunger center and a thirst center. And when it activates that thirst center, it's banking on the fact that you're going to reach over and grab a bottle of water and drink it. Unfortunately, that's not how we are in our current society, or at least our U.S. society. When we get thirsty, a lot of times we reach for everything but a bottle of water. Also, a decrease in glomerular filtration rate is ultimately going to decrease the urine output to maintain blood volume and blood pressure. So it's doing everything that it can to try to help out. And then the last thing, of course, is vasoconstriction, which if we can constrict the local blood vessels, specifically things like the afferent arterioles there, if we can constrict those blood vessels, we can reduce the diameter that the blood is flowing through, which will increase resistance, which will increase blood pressure in this area. So now we look at angiotensin 2 in a low blood volume situation. Angiotensin 2 shows up, and we look at the angiotensin 2. We look at it's the receptor that kicked it all off. And we look at the control center. It's just like we were saying in the previous picture, except this just makes it a little more up close and personal. Oh, I want to talk about this for a minute. Diabetes insipidus. Diabetes insipidus can occur because you're overproducing ADH. Because remember, ADH says antidiuretic hormone. Excuse me, not an overproduction of ADH. I'm sorry, an underproduction of ADH. So what winds up happening is your body, instead of responding to ADH, utilizing ADH, and uh, retaining water like you should when you need it. Instead, it's dropping off water. It's throwing it away, and it's throwing it away by huge amounts. Remember, when we saw the original picture, we were putting out water by like 1.5 liters a day. This person who has diabetes insipidus is putting out urine at 20 liters a day. I mean, they can stop drinking and eating for the entire day, and they're still urinating like they've been at a drinking party. Really sad. And did you notice that it's called diabetes? There are numerous different types of diabetes, not just diabetes mellitus. Now, let's see. Got a little problem here. I'm not seeing the slide that I want to use. Um, I'll keep going until I get to this one. This one is talking about A and P, and it's actually not one of the ones that I wanted to talk about. Um, I got a little lost here, but I'll go with it since it's here. Um, Notice that the stimulus here is increased stretch receptors um, here in the atria. They're baroreceptors here in the atria. So in the atria, if you remember the heart, the atria are the chambers that receive blood. Ventricles are the chambers that send blood out of the heart. Atria are the ones that receive the blood in the heart. And so we're getting an increase of stretch baroreceptors in the atria. That's not good. Okay. Because if we've got this, if our atria are being stretched, then that means the amount of blood coming back to the heart is coming back with too high of a force. There's too much pressure involved, which ultimately means we have high blood pressure. So the question now is, how do we get this blood pressure to drop? All right. So the receptors, the baroreceptors in the atria, they respond. They ultimately respond to the stimuli, and what they do is they send signals, and the atria wind up releasing ANP into the blood. So the cells wind up releasing the ANP into the blood. You can see the little triangles there, and once that ANP hormone floats through the blood and it reaches its targets, you can see the effectors, the targets of ANP. One of the things that's going to happen is right off the bat, vasodilation. Because if you do vasodilation, you dilate the blood vessels, you cause the lumen space and the volume inside to increase. And anytime you increase the volume of a fluid, anytime you increase the volume in a space that a fluid is passing through, the pressure that that fluid is producing is going to rapidly drop. So we increase volume, we decrease pressure inside the blood vessels. So blood pressure starts to automatically go down. You'll notice that the kidney image, it says that there's increased glomerular filtration rate, increases the urine output to decrease blood volume and blood pressure. So it's concerned saying, okay, this is how we're going to deal with this. What we're going to do is we're going to increase the amount of filtrate that the glomerulus is putting out. And once it does that, then we can use that filtrate, we can put it through the nephrons, and ultimately that filtrate will become, it'll become urine. And that means that that will be more fluid that we're getting out of the body. And then the third thing is increased loss of sodium and water in the urine, decreases the blood volume and blood pressure. Anytime you throw away sodium, water is going to want to follow that sodium because it's an electrolyte, it's a salt. So water goes where salt goes. If we can manage to throw salt away, then ultimately we wind up throwing water away as well. And then the last thing is that we see a decreased release of renin, uh, and a decreased release of aldosterone and ADH. So we see those three hormones kind of take a sideline to being released at that moment in time. So when we start talking about dehydration and we start talking about overhydration, dehydration is usually referring to water depletion. In other words, you don't have enough water in the body. Why? Well, number one, inadequate water intake. If you're waking up in the morning and it's 5 and 6 in the morning and your urine's kind of dark, no need to freak out because you've been lying in the bed. Your kidneys have been working the entire time you've been in bed. You've been asleep, so you couldn't drink water. But if it's 2 in the afternoon and your urine is coming out the color of one of your favorite college football teams, like it's coming out the color of the orange of Syracuse or Clemson orange, or something like, or even Tennessee orange. All right, if that thing's coming out dark, then you got a problem. You're not drinking enough water. So one of the first ways that people get dehydrated is inadequate water intake. They don't drink enough water. And no, water in your coffee and water in your tea do not count towards just drinking straight water. All right. So another reason why a person could be dehydrated is because of fluid loss, the throwing up. If they're vomiting, they're going to lose a lot of fluids. That's why you got to be very careful when someone has spent a lot of time vomiting. They lose a lot of fluids, and you notice that when that person starts losing too many fluids, they start getting even more sick. Same thing with diarrhea, runny defecation and diarrhea. The person's not reabsorbing all that water. They're losing a lot more water than they think. And then, of course, inadequate ADH. That might be a hypothalamic pituitary malfunction, might be a problem with the hypothalamus and the pituitary gland. If they're not producing enough ADH, which is anti-diuretic hormone, which tells the nephrons, reabsorb the water, please and thank you. And dehydration can ultimately lead to sodium levels that are just too high, which causes disease and disorder. It can lead to you being thirsty, which is normal, but then it can also lead to wrinkled skin, which is not so normal. You've probably seen people who never drink water, and they're dealing with their face looks great because they got just the right makeup on and everything. But then you look at like their fingers and you look at their knuckles, and they're really wrinkled. They're dried up. That's because of the dehydration they're going through. Another thing that can occur because of dehydration is you wind up having a decreased blood volume and blood pressure. And why? Because you're not putting any water in there. And one of the things that's a driving force for blood pressure is blood. And the part of blood that's liquid is blood plasma. So you don't drink water, you don't increase your blood plasma, therefore not increasing whole blood, therefore decreasing blood pressure. And yeah, you get the point. And then the last thing is a fatal circulatory shock. That could be really bad. Now, of course, that's not going to happen by you only drinking 2 bottles of water a day. That's something more you're going to see out in the desert. But hey, it can happen. And then last but not least is overhydration. That's when you have excess water. And of course, it's due to excess water intake or chronic renal failure. Sometimes people, they start experiencing chronic renal failure. The kidneys start going out, and they're not producing the amount of urine that they're supposed to. And sometimes people don't even think about it. They don't even pay attention to the fact that they haven't been urinating nearly as frequently as they should, and yet they are drinking plenty of water. They're drinking plenty of water. They're taking in plenty of food. Everything seems okay on the front end. They don't realize that the reason why everything's happening the way that it is simply because they're not getting enough. They're not getting rid of enough water. All the water that they're taking in is just sitting inside of them. There could be possibly an excess of ADH. Maybe it's hyperreacting, overproducing the hormone, therefore leading to a series of overhydration events. And then this excess water intake, I just skipped over it a bit. One of the things that the notes brings up in the textbook brings up is water torture in hazing rituals. That is a example. It's crazy because you still got fraternities and sororities still hazing folks like nobody's business. I guess they all think that they're going to be the one that doesn't get caught, but they're getting caught left and right. Um, Marathon runners and paddlers, these people have to be real careful, especially, the Ironman challenge and all that stuff. And then people who take ecstasy, um, they're trying to compensate for their enhanced thirst, and then they wind up overhydrating, and doing some serious damage, if not killing themselves. Um, and so this can lead to a lot of dysfunction in the body. Everything from sodium levels that are way too low, um, increased blood pressure and blood volume because of all the excess water, and then central nervous system simple symptoms like water intoxication, which can even wind up in convulsions, coma, and worst of all, death. So that's all we're getting into on this video. Just wanted to kind of talk about more so the reason as to why um, we have to be concerned about electrolyte balance and fluid balance. We'll get into some more topics in a little while. So hope that helps you guys out a bit. See you later.